All right, hello everyone. Thank you so much for joining us for another NEARC community event. My name is Katie Grillo and I'm the GIS Web Technology Specialist at the City of Cambridge. I'm also an adjunct professor at Jefferson University and the NEARC board president. So we are here today for another NEARC community event. These are online sessions that we've been hosting between our two major conferences to bring people together to talk about a specific topic, share ideas, connect with one another, that kind of thing. So just a little bit more about NEARC before we dive in today. I just want to say we are the Northeast ARC Users Group. We host 2 conferences every year in the Northeast. We have a 1-day event in the spring and a 3-day event in the fall. This year's fall event is going to be hosted up in Brentwoods, New Hampshire. So we'll be at the Mount Washington Resort, and that is from November 6th through the 9th. And the call for abstracts is currently open. So I encourage you, please, if you have a presentation or something that you're interested in sharing with the community, then please consider submitting your abstract. I'll ping a link or put a link in the chat after towards the end of our event today. So as I mentioned, we're here for a community event. Just a couple logistics. I will be doing my best to monitor the chat. If you have any questions or concerns, go ahead and post those into the chat. I've got Tom Schwartzman and Mark Scott here from Esri to assist with that. Hello, thank you guys. So you can put questions in the chat, any comments in the chat, and we will leave some time at the end for Q&A. As I mentioned, this session is being recorded. I will send a follow-up email with the link to the recording, as well as a list of some resources that our speaker has pulled together for us. So fear not, you don't have to worry too much about taking too many screenshots and that kind of thing. We'll definitely send you resources after the fact. So today we are joined by David Yu, who's coming visiting us from Redlands. So thank you, David, for joining us in the morning over there. Excuse me, David is a senior data scientist at Esri, and today he's going to help us explore GeoAI. So this is a new topic for me, so I'm not even going to try to explain things. I'm just going to kick it over to David.
Sounds good. Thank you so much. So let me share my screen here. Okay, so GeoAI, and as Katie mentioned, this is a fairly interesting topic. I think this is an emergent field, although the individual fields of artificial intelligence and GIS obviously has been around forever. So I really want to dive deep into some examples today, some demos, and show you what is the art of the possible when it comes to GeoAI, and what are the different use cases that we can see for GeoAI, and also for anyone who's technically inclined, I might even show some interesting snippets on how you can use GeoAI through things like the Python API or through ArcGIS Pro. So before diving into GeoAI, I really want to clear up a few terms, because especially in the field of artificial intelligence, I think all of us heard about AI, deep learning, machine learning, and sometimes these terms get used interchangeably, where they really mean different things depending on the scenario. So I want to take a step back and just quickly address these 3 terms and what they mean in the context of GeoAI. So when we talk about artificial intelligence, we're really talking about this broad capability where we're trying to have machines perform tasks at the level of a human, if not better. And you can think of things like IBM Deep Blue, which beat Garry Kasparov in chess way back when, I think it was 1997. Or you can think about some more recent advancements, like all of these interesting capabilities coming out of natural language processing, with machines being able to formulate sentences. Or if you think about something really simplistic like automated feature extraction, that's all an example of artificial intelligence. And then machine learning is really a specific implementation of artificial intelligence that's all about learning from large quantities of data. So machine learning is something that's come about in the past few decades or so, but really it's only in the past, I think, 10 years where we've seen a huge advancement in the field of deep learning, which is yet again another specific implementation of machine learning that's all about leveraging the power of deep neural networks. And what we mean by deep learning is the capability of having machines being able to ingest high-dimensional data. So these are things like images, videos, text, and even unstructured data like LiDAR point clouds. And so when we talk about GeoAI in the context of sort of GIS, we really mean a combination of both machine learning and deep learning. So we do have machine learning and deep learning capabilities that are embedded across our GIS. And I do want to mention that it is embedded across all of our suite of tools and capabilities. It's not a single product that you can put a finger on. It's more of a capability that you see through the Rgs API for Python, through Rgs Pro, through Rgs Online, Enterprise, and so on. And then we're continuously adding new capabilities, new models, almost every single week, particularly to the Rgs API for Python. So what can machine learning do? And I think this is a fairly interesting question because a lot of it really depends on the complexity of the problem that we're trying to solve. But in general, machine learning capabilities can be divided into, I would say, 5 key tasks. The first one is for automating feature extraction. And this is super interesting because starting from 2015, we in the machine learning community have begun to see AI models really outperforming human benchmarks on things like object recognition and semantic segmentation and so on. So, by training a machine learning model to be able to detect these kinds of features, we're not only enabling them to perform this at a very large scale, which is obviously the appeal of using these kinds of AI models, but also sometimes, as long as your training data is good, then these kinds of models can even outperform human annotators, which is pretty cool. And the good thing is that these kinds of automated feature extraction workflows are not necessarily constrained to a particular data type. The obvious one being imagery. And within Esri, it's all about nadir imagery, right? Things from a top-down angle. But also we have models that are able to extract features from oblique images, from oriented images, and also from things like LiDAR point clouds as well. And later we'll see how we can leverage some pre-trained models that are available on the Living Atlas for us to be able to perform this type of work very easily. So that's the first key task. The second one is all about making predictions. For instance, predicting water pipe failures, depending on whatever historical data that we have access to, or being able to predict the likelihood of an accident on certain roadways by taking into account weather factors, temporal factors, also physical factors like what is the curvature of the road, how many lanes how many lanes there are on a road, and so on. And the power here is that we can potentially make use of tens or even hundreds of different attributes in order to make a prediction in a way that it's almost impossible for a human to be able to do. The third key task is finding patterns and clusters. And this is particularly important if we're unable to find any patterns visually, because that's what we as humans can do fairly simply, is look at a visual pattern and then determine if there is some kind of clustering going on. But if we don't have access to good visual representation of our data, then we can always just feed it to a machine learning model for it to be able to do the same. And then somewhat along the same lines, detecting anomalies as well. Anything that doesn't fit into a pattern is considered an anomaly. So that's the fourth key task. And then finally, something that's more recent is extracting insight from unstructured text. So there's actually a ton of GIS data that's embedded in text, particularly location data. When something happened, what happened. For instance, if you think about a fire report, right? How many fire engines were in attendance? What type of fire it is? These are all insights that are embedded in text. And traditionally, if we're able to make sense of it, we have to literally have someone sit down and read through the individual lines to be able to understand what's happened. But with machine learning, particularly with natural language processing, we can feed all of these text data, these forms, into a model for it to be able to drop points on a map to indicate where something happened, but also try to extract certain insight from that text, what happened, how many fire engines were in attendance, and so on. So these are the 5 key tasks, and these are all things that you can do today through ArcGIS, whether it's through Rgs Pro or through the Python API and so on. And I just want to quickly mention that it's depending on what it is that you're trying to do, AI is really infused within our suite of tools and capabilities in different ways. So for instance, through Survey 123, you don't really get to train any kind of AI model. Rather, we have the ability to ingest models that you've already trained using either the Python API or through ArcGIS Pro. Whereas if you're interested in training your own model based on your own data, then we recommend two routes. First is using the ArcGIS API for Python. The second one is using ArcGIS Pro. And these are generally used interchangeably because all of the machine learning models and also the training capabilities that we have exposed through the Python API is also available as a codeless experience through ArcGIS Pro. So that just makes it a lot more convenient. What we're really trying to do is make sure that data science and machine learning is something that can be accessed by folks who are not necessarily experts in the field. You don't have to be a data scientist to really know how to train these kinds of models and to use these kinds of models. Okay, and it's impossible to talk about machine learning without mentioning the life cycle because all of our machine learning models experience the same life cycle. We always begin with the data prep step. And I guess I should preface by saying that there's different types of machine learning because depending on what is the data you have access to, the model can learn in different ways, right? You can provide ground truth labels to the model, which is what we call supervised learning, or you can have the model try to figure out what is the right answer, and that's unsupervised learning or semi-supervised learning. Today, we're just going to be focusing on fully supervised learning. And so we're teaching models through examples. And the way that model learns is by providing good examples. So you want to make sure that almost 80% of your time is devoted to data prep. And this is pretty interesting because going into this field, a lot of people might get the false impression that what AI and deep learning is all about is building models. Well, it's really not. It's really 90% doing data cleansing, data cleaning, ETL type work. And so it's important to be able to understand the concept that, if you have a very good model and you don't prepare your data properly, then it's garbage in, garbage out. You're just going to get a bad result in the output. So data prep is super important. And sometimes that means sitting down and manually annotating and labeling the sorts of things that you would like the model to extract. And then the second step is training that model. So providing your data in a way that the model can then ingest. And we'll see in a few examples later on how that is done. Third step is inferencing. So this is also known as prediction. So this is where once your model has finished training, now you're interested in having this model make some kind of prediction over ideally a different area of analysis. And this is, again, something that can be done either through a codeless experience through ArcGIS Pro, or if you're someone who is, let's say, Python savvy, then you could also do this through the ArcGIS API for Python. And then finally, really, making use of the outputs of the model by, pushing everything through to an information product like ArcGIS dashboards or web app or some kind of web map is in the final step. Okay, I really don't want to cover any type of theory, although I think it is important to have everybody understand exactly what is a model and how it learns so that we're not really treating this as a black box. So I'm trying to simplify this in these slides here. So if we think about a model as just a kind of generic function that's able to take in data and label pairs, then what the model produces in the output is some kind of learning signal that it can use to be able to tune its internal parameters. If you think of a model as a box with a ton of different knobs inside that can be turned according to how well it makes a prediction, then the training process is really all about turning those knobs internally so that the model is able to learn over time. And then finally, at inferencing stage, what happens is that we only need to provide the raw data to the model. We no longer are concerned about the labels. And if the model is trained properly, then it's going to be able to make a good judgment on what it thinks the label should be. To sort of put this in a more graphic context, let's think of a model as something that we call a learner, right? A learner is a very simple-minded thing that's able to learn from examples. And the type of examples that we're going to provide the learner is either text examples, tabular data, vector data, or things like unstructured data like LiDAR point clouds, or your classic imagery example, so imagery from nadir or oblique images. So that's your raw data, but all of that raw data has to be paired with something, and in that case, it would be your ground truth labels. So as an example, if we're interested in having a model predict the brand of cars according to attributes like curb weight, engine capacity, and horsepower, then engine capacity, curb weight, and horsepower would be your raw data, and then the label would be the brand of car that you would want the model to predict. Another example, if you're interested in performing segmentation or classification on top of point clouds, then you need to be able to sit down and then manually classify some of those points according to the different labels that you have. So for instance, green here represents vegetation, you have brown for ground points, and then red for building points. Another example is if you're interested in having a model come up with precise geometries around building footprints, well, then you have to be the person to sit down and then draw those geometries as an example and provide that to the learner. And then finally, for very simple classification examples, if you just want the model to understand what type of flower is being shown here, then you have to provide some training examples too. So during the training stage, what happens is that the model is going to take that data and label pair, and then it is going to, first of all, make a really rough prediction on what it thinks that label should be. So the model is going to only look at that data first and try to make some kind of prediction for that label. And because the model hasn't been trained before, obviously these labels are going to be quite bad, as you can see here. But the model is then going to turn around and take that ground truth label and then compare it with the predicted label. And in doing so, create some kind of loss. And this is a simple measure of how well that model is doing. The model is going to take that loss and, as I've mentioned, tune its internal knobs and parameters so that it does better in the future. And we're not going to cover how that happens under the hood, but it's basically turning some knobs under the hood. So that's the first step. And in the second step, the model is going to look at another set of examples. So it's going to take a look at another image, another label. It's going to make another rough prediction, try to take that label, compare it with its own prediction, come up with a loss, train its internal parameters, and so on. So that's what we call one iteration. And you'll see this term come up later when we use ArcGIS Pro to train a model. And typically it would take hundreds, millions, tens of millions of iterations for the model to converge or for the model to get to a point where we think it's ready for prediction. And once it's ready for prediction, then it's a very simple task of simply providing that raw data to the model. And then the model hopefully is going to spit out something that resembles a good building footprint. So we've talked about the life cycle of a model, but to put it in terms of computer vision and feature extraction from imagery, the example of data preparation would be, first of all, getting access to your imagery data, bringing it into ArcGIS Pro, using our various labeling tools to draw either bounding boxes or bounding geometries around whatever object it is you want to extract. And then data prep is a simple geoprocessing tool that you can run that would turn all of your imagery and your labels into a format that the machine learning model can understand. Training is something that can be done completely within ArcGIS Pro. It can be done through yet another geoprocessing tool. Or if you'd like, you can also do the same using the Python API. Same goes for inferencing. And then finally, once inferencing is done, then your model is going to produce a series of bounding boxes over the test imagery that you send it. Before we dive into some demos, I just want to quickly cover 5 key tasks when it comes to imagery deep learning, because I think it is important to go through this. So when it comes to imagery, there's actually a different whole host of different things that we can do with our deep learning models. The first is called pixel classification. Now, in the world of machine learning, this is also known as semantic segmentation. But what it really is simply assigning class labels on a per pixel basis. So for instance, if we take a look at this image here, we see that roads and buildings have been assigned unique colors according to what type it is. The second example is object detection. So this is all about returning minimal bounding boxes over your objects of interest. So in this case, we have bounding boxes over palm trees, but this could easily transfer to creating bounding boxes over airplanes, cars, pedestrians, what have you. The third example is instant segmentation. So this is really combining the best of both worlds between pixel classification and object detection. One of the issues with pixel classification is, I don't know if you can see this, but if we take a closer look at these two buildings, they've been classified as one contiguous blob. So the model has no understanding that these are two unique instances of houses. Well, if you're interested in dropping a pin above every house, maybe you also want to do object detection. So this is where coming up with some bounding boxes over those pixels is also helpful. So that's what instance segmentation is. For those of us who've seen Silicon Valley, image classification is your classic hot dog, not hot dog example. So very, very simple, coming up with a label over each image tile. And then image translation is a new capability that we've added, I think a few years ago. This is quite interesting. I don't know if you can see this, but we're able to do things like take images of zebras, turn it into horses, and back. So you might be wondering how this is relevant to a GIS use case. Well, we could take something like RGBD imagery and then turn it into a SAR representation and back. Or we can do this between different types of imagery, right? So we can take RGB, convert it into just a normalized DSM layer, and back. So that's actually pretty useful if you don't have access to the type of imagery that you want. You could actually use image translation to help you fill in some of the gaps. One thing I do want to quickly mention, obviously not everybody is going to be interested in training a model from the ground up. Some of us just want to be able to leverage existing models, and we do have access to those. So if you go to the Living Atlas and search for deep learning as a keyword, then you're going to find, I think, something like 27 to 30 pre-trained models that we've made available through the Living Atlas. And this is a list that's constantly expanding over time. And if we take a look at some of these models, we see deep learning models that help you, generate building footprints, that help you perform land cover classification, tree point detection from LiDAR, and so on. Really, it spans a lot of different types of data inputs. And these kinds of models are also really, really good because generally they've been trained across a very large data set. So even if you don't have your own existing data to train a model with, you could always just download one of these pre-trained models and then run it out of the box, which is pretty convenient. Okay, I just want to quickly cover some broad examples before diving into hands-on demos. So just to give you a sense of what it is that we can do through these kinds of machine learning models. Well, the first one is object detection from imagery. This is no doubt something that you're all familiar with already. But in this case, we're trying to understand parking lot occupancy. So we've trained a custom model to be able to detect cars and also classify them into different types of cars, which is pretty cool. Second example is high resolution land cover mapping. And I might just zoom in here so you see a little bit better. So this is all about having a machine learning model perform pixel classification. So now this time we're assigning unique class labels on a per pixel basis. And then we see that roads have been assigned a particular color, high vegetation have been assigned a particular color, fields have been assigned a color, and so on. Another example would be object detection from videos. So what we see here is a CCTV camera that's been deployed in Jackson Hole, Wyoming. And we see that as cars pass by the CCTV camera, it's being detected and classified into cars, buses, pedestrians, and so on. And then on the right, we see a little dashboard that is simply performing car counting. And then you can probably see how easily this could be extended across multiple roadways and multiple intersections, where once we have an idea of what is the baseline amount of traffic that we expect to see at a given intersection, we can really start building off a anomaly detection pipeline. I'm not sure if you can see this clearly, but I'm going to skip to a point and then zoom in here. These are about 100 different cameras that are deployed in downtown DC area. And we've definitely noticed some anomalies along the main street where there's an overwhelming number of pedestrians that are being picked up. And it turned out that this was a parade that was happening at that time. So this is the type of insight. The downstream analytics is very, very important here. This is the type of insight that we can get from automating feature extraction through machine learning. Okay. Some pretty cool stuff that we've done in the past is accidents probability prediction. So as we know, there's a ton of different causes for accidents, some of which are weather factors, right? What is the amount of rainfall, how cold it is. Also human factors, like how fast people are driving on average along a certain roadway. And also physical factors like what is the curvature of the road and so on. So using all of that, we can actually train a model to be able to predict what is the likelihood of an accident along given roadways. So if we take a look, I'm just going to pause it here. If we take a look at this dashboard, what we've done is color code every single intersection according to the likelihood of an accident. And then the red dots that you see here are locations where accidents actually happened. So it actually conforms pretty well to our prediction. Here's another example for ETA prediction. So some of us might be interested in understanding if I leave my house at a particular time, how far can I travel in any given direction? So this is what ETA prediction is all about. You can drop pins anywhere on a map, and then we have a model that predicts in a 25-minute window how far a car can travel. And this is what you see here. These are ISO contours on how far a car can travel in a 25-minute window. And we see a little timer on the bottom left where during midday, during rush hour traffic, these ISO contours really start to shrink because we can't get very far. But during nighttime, you can go pretty far. Smart road digitalization, here's another pretty cool example. So this is actually using genetic algorithms to be able to digitize roads. So the points that you see on the map here, these are GPS breadcrumbs that are left behind by mining vehicles. And obviously this is a location where we don't have many built up roads. So we're interested in digitizing these roads and putting it on a map. So the genetic algorithm here is simply finding the most probable path that connects all of these different breadcrumbs together. And then as you can see over time, it is adding new branches as needed and contorting some of these lines as needed so that it fits better to the existing data. A few more examples, Kfo Site Detection, so that stands for Concentrated Animal Feeding Operations. These are actually a huge source of pollution, especially to groundwater. So it is important for compliance purposes to be able to detect these Kfo sites, especially if they're illegal sites. And this is an example where it's kind of interesting because there isn't necessarily a single feature that you can visually identify that marks a particular complex as a Kfo site. It's really a combination of different things. For instance, you have to be able to find some kind of barn-like structure. You have to be able to find some kind of water treatment facility, and so on. But the great thing about computer vision models is that it's very good at generalizing. So as long as you provide sufficient examples to the model, it's going to be able to gain some kind of intuitive understanding of what are the different features that comprise a Kfo site. When it comes to 3D data, so LiDAR feature extraction is one thing, but we're also able to do things like 3D building reconstruction through LiDAR, which is pretty cool. Reinforcement learning, this is just purely experimental stuff, but we're able to do things like understand what is the best way to allocate public resources, like fire engines or police patrol cars, in order to maximize or minimize some kind of metric, right? So for instance, if we're interested in minimizing response times to 911 calls, we can actually train a model over a period of 100 years to be able to gain an understanding of, what is the average speed these patrol cars should be traveling at, what are the different areas that they should be going to, should they turn on their sirens, and so on. When it comes to video, another pretty cool example is object tracking and anomaly detection. So object tracking is something that we can do using full motion video inside ArcGIS Pro. And we can also do this through drone feeds, as you can see here. So these are cars that are being tracked. And if they're going over the speed limits, we actually have a little red warning box here. And then also their paths can be tracked as well. Disaster response. I'm not going to talk about that just yet because we're going to dive into a hands-on exercise using that. Just another example for video, we're able to consume oblique images as well. So this is just a dash cam that's been mounted on a car, and we're able to detect different types of road cracks. So for those of you who don't know, there's actually completely different categories of road cracks like longitudinal cracks, transverse cracks, and so on. And it's important to be able to classify them, which is what we're doing here. Okay, not going to go over too much of those examples there, but I just want to reiterate that in order to have access to these kinds of deep learning capabilities, there's really two routes that you can take. The first one is a no-code experience through ArcGIS Pro. So these are a series of geoprocessing tools for you to be able to, first of all, create your training data, and then exporting it into a format the model understands, and then training your model. Once that model is trained, you're going to receive a model weights file that is simply a representation of the different knobs that the model has been tuning that you can then send to our list of inferencing tools or prediction tools to be able to make prediction over new imagery. And then the exact same things can be done through the Rgs API for Python. The great thing about using the Rgs API for Python is that whenever new tools or new models come out, typically they would come out on the Python API first, and then they get filtered down through the Pro tools. The other great thing about the Python API is that they tend to be a little bit more extensible compared to RGS Pro. We do expose a few more parameters through the Python API. And then if you're someone, again, as I've mentioned, who is Python savvy, that you can really train a model throughout the RGS API for Python a lot quicker than you can do through RGS Pro. Okay, so with that, I'm going to jump into some demos here. And again, if there's any questions, feel free to write it down in the Q&A chat box. Okay, so for the first
David,
demo,
just a reminder too, I do have the polls for you if or when you want to put those out. I don't know if you were saving those for the end for discussion.
I think we can have the polls out now, actually.
Sure. Okay. I have to do them one at a time, so I can do, I think. So it looks like we have most people have answered. So I'm going to go ahead and end this poll and share the results. So the first question was, what is your level of familiarity with GeoAI? And it looks like we do have 3 people in the audience who said that they've applied GeoAI workflows. So maybe if we have time at the end, we might ask folks what those are, just out of curiosity.
Perfect. Yeah, it looks like a mixed bunch. There are a few people who's not familiar with AI, so I feel a little bit better that I've gone through some basic concepts. Okay, should I continue or are we waiting for more polls?
I can go ahead and put the second one up if you want, and then maybe
Okay.
we can save the last two for the end. So the second question is, what would you like to see GeoAI achieve? And if you put other, then maybe you can put that in the chat of what your other dreams might be. Got about 80% of people submitted. So I'm going to go ahead and actually give another second. Seems like there's more coming in. All right, I'm going to end this poll and then share the results. Seems like a very mixed bag here, which is, what do you think, David?
It is really good because I think I do cover all of those examples in the upcoming demos. Most of my focus is going to be on imagery feature extraction, simply because I think it's the easiest to show. Although a lot of our other capabilities, it's really the same process to be able to train a model and to run it. So I will be going over those.
Great, thank you. Yeah, we do have 2 more polls, but maybe we can share those, save those for the end.
Yep.
All right, thank you.
Sounds good. Okay. So before I dive into the demo, I want to share a quick resource with everyone. So if we all go to Google and search for Learn ArcGIS, I would say this is probably the best resource if you're just getting started and you want to try some hands-on exercises for using GeoAI. So if we go to the first link, Learn ArcGIS, and then click on Search All Content, the keyword here is deep learning. So if we go to deep learning, we'll see a ton of examples on different use cases for using a machine learning model. And the one that we're going to be covering right now is actually in here. It's called Automate Fire Damage Assessment with Deep Learning. So these are fully annotated lessons that you can follow along, and then all the data is made available to you if you, as long as you have access to ArcGIS Pro, you can run along, this demo alongside us, and then it's very well written. And then there are a few prerequisites that I just want to quickly talk about for running any deep learning workflows. And that is, you first of all must have access to a GPU on your computer, especially a CUDA-enabled GPU. It is possible to run through these exercises without a GPU, although you might find it's going to be a lot slower. But if you are interested in figuring out what type of GPU you have, it's very simple. Just right-click on your toolbar, go to Task Manager. And then if we go to Performance, you should be able to see your GPU here. And hopefully it's going to be an NVIDIA GPU. And you should be able to see things like your memory consumption and everything here.
Can you run through that one more time, David? What did you do?
Sure.
You right-click?
Yep, just right-click on your taskbar, go to Task Manager. If you're using Windows 11, I think it's going to be right-clicking on the Windows button instead. And then if you go to Performance, you should be able to see. So there's 2 GPUs in here. First of all is the integrated Intel GPU, but we're interested in the discrete GPU here from NVIDIA. So we just want to make sure that it is available. So that's the first thing. The second thing is to run through any of these examples, we have to download some prerequisite libraries, and that should be available also in the Learn lesson here. Let's see. Or maybe it's not available, but the way that we would find those libraries is very simple. Is if we go to Google and search for ArcGIS, deep learning, GitHub, it's going to be here. It's an installer that you can just click on, and it's going to install the libraries for you. The reason that we have them shipped separately is actually because of export control compliance, that we can't include these libraries along with ArcGIS Pro. This is something that you have to download by yourself. But depending on what version of Pro you have access to, you can simply click on one of these download link. It's going to provide you with a executable file. And then if you unzip this folder, it's going to contain an executable file that you can just click, and it's going to make that installation for you. I'm not going to show this here to save us some time, but just letting everyone know that this is here. Okay, so with that out of the way, I want to quickly talk about the demo. And I want to begin with the final information product first. And so this is the Woolsey fires that happened in California, I think back in 2018. And this is a particularly bad fire that ended up with, I think, more than 300,000 people evacuated. It affected LA, Ventura counties in California, really burnt down a lot of buildings. And in situations like these, especially after natural disasters like hurricanes and wildfires, what happens is that agencies would go out, fly aircraft or drones over the affected regions. And typically, these images would then be processed by analysts who are sitting down and then manually labeling these buildings as either damaged or undamaged. And you can imagine that these folks are operating with not a lot of time on their hands. Whereas, this really is a critical situation. You want to have these classifications be made in a short amount of time over a very, very large extent. So this is actually perfect for deep learning to come in and perform this type of extraction automatically. So if I turn on one of these layers, we'll see the end result for running a deep learning model on feature extraction. So in this case, we do have access to the underlying building footprint layer. Although even if we don't have access to the building footprint layer, we can simply bring in another tool to create these building footprint polygons, and then yet another model to go ahead and classify them as either damaged or undamaged by a fire. And the great thing about these kinds of end information products is that they can really put things in context, because we get an understanding of not only what is the number of damaged buildings, but what is the estimated dollar amount in damages that are caused for any given areas that we navigate to. And that is very useful, obviously, for insurance purposes, but also just understanding, the severity of damage. That also is very helpful for a rescue, from a rescue perspective. So you understand what are the areas that you really need to prioritize sending your resources. So this is what we're going to build in the next, I would say, maybe 10, 15 minutes. And the way that we're going to do that is through ArcGIS Pro. So I really want to show you the codeless experience first before we go to any of the Python first experiences. So as with any deep learning model, we need to be able to provide some kind of training data. So again, remember that this is supervised learning. The model is learning from examples. So what we're interested in is providing these kinds of ground truth labels to the model in order for the model to be able to make a prediction over a different area, which is these blue buildings over here. Now, we've already gone ahead and assigned class labels to these buildings according to whether or not they're damaged. But it is important to be able to also validate that training data, because as I've mentioned before, garbage in, garbage out. Even if you have a very good model, if your data set is shoddy, then your results are not going to be very good either. So one of the things we can do is, if you just click on attributes, click on layers, we can select the layer that we've made to be our training set. And we can actually jump through some of these examples to visually assess whether or not these classifications are correct. And in this case, we see that there's actually a misclassification here, item number 8. It's been classified as undamaged, whereas it's really a damaged structure, as we can clearly see. Now, if we have access to, let's say, 100, 300, maybe 1,000 such examples, having a single misclassification in our training data, honestly, is not going to make a lot of difference. However, if we kind of scroll down, okay, yeah, we do have a few thousand examples. So yeah, it's not going to make a huge difference, but nonetheless, it is nice to be able to make sure everything is correctly classified. So I'm going to go ahead and set this as damaged. I'm going to click apply, and you'll see now this is correctly classified. So if we go to the next example, we'll see another instance where we have misclassification. So I'm going to set this as damaged, apply, and go to the next one. And this is erroneously classified as damaged, whereas it's clearly an undamaged house. So I'm going to correct that as well. And well, it turns out there's actually a lot of really bad data here. So this is why it pays dividends to be able to go in and make sure that we validate all of our training data. And in these other examples, we see that the data is roughly correct. So we're good there. Okay, so now we've assessed our training data. The next step is to actually export that data into a format that the model understands. Now, I keep saying that because we can't just feed an entire imagery layer into the model. Typically, these kinds of deep learning models, they only ingest image tiles that are up to, let's say, 512 by 512 pixels. Or if you have a very good GPU with a lot of onboard memory, something like 1024 by 1024 pixels. But nonetheless, that's a lot smaller than this image that we have here. So what that export training data process is doing is simply taking your imagery and your labels and then tiling it up into smaller representations. So that is going to be a geoprocessing tool that we can run. So if you click on analysis, go to tools, and let's search for export training data for deep learning. And by the way, these tools are available through the Image Analyst extension on ArcGIS Pro. So if you have something like Pro Advanced, then you should have access to all of these tools. Okay, so this tool is asking us for, first of all, the input raster. So I'm going to drag in our raster. I'm going to specify a location where we want these examples to be stored. I'm going to create a new folder called Export Training Data 2. And the input feature class is simply going to be our training sample. So I'm going to drag that in. But at the same time, I'm also going to open up the attribute table so we can take a look at where the classification is stored. So in this case, the classification, the class value, is stored in this attribute called class value. Now, typically, we want to make sure that the different classes are represented as unique integers. In this case, it's actually unique integers under the hood because we've set a domain value for these. So undamaged, I think, is 0, damaged is 1, something like that. So the tool is sort of smart enough to understand that what are the valid class value fields that we can choose. So we can go ahead and select class value. And for input mask polygons, we don't have to worry about this. What this is doing is basically, if we're only interested in exporting data from a specific location, we can send that polygon over here. For the image format, I'm going to leave it as default. And tile size, stride size, this is just all about, how many tiles over, for every single image chip, how do you want to move that sliding window to create the next image chip? So I'm going to leave it as is. And that's about it. Now, one important thing to note here is that you want to make sure that whenever you're exporting your training data, you have a cell size that is consistent to the cell size of the imagery that you're using whenever you're performing inference. So this is important because the model generally gains an understanding of what are the different features at a specific scale. So for instance, if I set the cell size to 0.3 here as I export my data, and later when I perform inference, I change it to a different cell size, then that has the effect of either zooming in or zooming out. And for the model, that's going to cause some confusion. So we just want to make sure that the cell size is consistent on the image that you're training the model with, as is on the image that you're performing prediction with. Okay, so this is running, but I just want to show you what that output looks like. So I've actually gone ahead and run this before. So let me bring that up. One second here. Okay, so what this is going to do is create a folder containing two subfolders. You're going to have images and you're going to have labels. So if I click on images, you'll see what's happening here is that every single house is now part of a single image. And I believe I can drag that in as well. And if I zoom into this location, you'll see that this house is being represented. And then in this case, if you've noticed, in one of the parameters, actually it should be label tiles. One of the parameters is blacken around feature, which is what I've done here. So that whenever the model tries to take a look at this image and decide whether this is damaged or not, it's not going to take into account the patch of pixels around the house. It's only going to look at the house itself. So that's the images, and then the labels are this a representation of the of both the bounding box around this of this house and also what is the damage classification. This is stored in XML format that I'm not going to open. Okay, I'm going to cancel this export training data process because it is taking some time. since I've already exported that before. But the next key geoprocessing tool here is called Trained Deep Learning Model. And this is a pretty universal tool in that regardless of whether you're performing object detection or semantic segmentation or object classification, it's really the same tool. You're all going to be using trained deep learning model. And if I expand model parameters and I click on this dropdown for model type, you see that these are all the available models that we have made available inside ArcGIS Pro and also for the Python API. And in brackets here, these models that tells you exactly what type of task this is for. So for instance, we have a few models for object detection, we have a few models for pixel classification, and so on. So this might cause a little bit of confusion if you're not particularly familiar with what these models are and the differences between them. So I'm just going to just quickly mention, for instance, for object detection, if you're only interested in drawing a bounding box around your object, single shot detector is a good one to use because it's a very lightweight model and it trains rather quickly. Now, in this case, because we are doing sort of hot dog, not hot dog, really there's only one model that we have available for this, and I believe it is called object classification feature classifier. Now, for this trained deep learning model tool, what we're going to do is we're going to take our exported training data, that entire folder, we can simply drag it in here. And the model is, this tool is intelligent enough to recognize what is the specific type of task that you're trying to perform. Because earlier, when we performed export training data for deep learning, we've set a variable at the very bottom that tells us exactly what is the type of work that we're trying to do. So if you remember, we selected, I think it was like tile classification. But then for other workflows, for instance, if you're interested in performing object detection, then it would be something like kitty labels or something like mask RCNN masks if you're interested in performing instance segmentation and so on. So the documentation is pretty rich on exactly what are the different types of hyperparameters that you can select there. And I just want to quickly bring that up too. So if we go to Google and search for ArcGIS API for Python, go to the first link. And if we click on API reference, and at the left pane here, we can select rgs.learn. So that's where all of our deep learning capabilities are stored inside the Python API. If we go to data preparation, in here, it's going to really in detail describe what are the different metadata formats that we can choose and the resultant types of workflows that we can enable using different types of metadata formats. So as an example, we've selected label tiles, and this is purely for hot dog, not hot dogs. And then if we're interested in something like, as I've mentioned, coming up with bounding boxes, then it would either be kitty labels, kitty rectangles, or Pascal VOC rectangles. So I recommend everybody to take a look at this page. It's going to be very helpful. Okay, you'll see that the model is hesitating a little bit here, and what's happening is that whenever we bring in our training data, it's actually going to download the trained backbone for the list of available models. So I'm not going to really run this trained deep learning model tool here, but just letting you know that's what's happening. So for all of these models, for the these come with pre-trained backbones. Okay, so you see here, if I click the drop down now, all of the other models go away, and we only have one left because it's recognized that we're interested in performing feature classification. And I'm not going to really fiddle around with any of these other parameters. Just one thing, whenever we run train deep learning model, we want to make sure that inside the environments tab, we select GPU as a processor type. And that is if you have an available GPU, because if you leave it as blank, it's going to default, I believe, to the CPU, and it's going to be an order of magnitude slower than if you were to use the GPU. Maybe I will just run this model really quickly to show you what the output looks like. Let me create a new folder. Okay, leave everything else as defaults. I'm going to change the batch size. So the batch size tells us for any given iteration, what is the number of images that you're going to feed to the model at the same time. This is a factor that simply speeds up training because a GPU can hold sometimes a ton of images at the same time. Although 64 is probably a little bit too large, I'm going to set that to 32 and click run. Now, once the model is training, you can click on View Details here. And this might take a little while, but what's going to happen is that as the model trains, you're going to see some metrics, very useful metrics that are being produced here. And there's two things here. One is training loss, and the other is validation loss. Not really going to explain what those mean in detail, but the idea is that you should be able to see both training and validation loss go down. And that's an indication that your model is converging or that your model is learning. So if you recall from the presentation slides, whenever that model compares its own prediction with the ground truth labels that you've provided, that difference is what loss is in a nutshell. So you should see those values start to decrease. Okay, I mean, this is obviously taking a long time, so I'm just going to open up the model that I trained previously and show you what the result looks like. So as the model is trained, you should receive a folder that contains, first of all, your PTH file. So this is where all of the internal parameters of the model are stored. You're also going to receive a DLPK file, and this stands for Deep Learning Package. So once you've trained that model, you can share that DLPK file across organization to your friends, to anyone who wants to use that model for either retraining or for inferencing purposes. But also another important metric that's being produced is this HTML file that I can double click. And what this is going to bring up is some diagnostics on the model, on how well it has trained. So this is the training and validation loss that I was talking about earlier. And ideally, you should see something like this, right? Both of them start to decrease over time as an indication that the model is learning. And you're also going to see some examples of model inference on unseen data. So for instance, the left column are the ground truths and the right columns are the predictions by the model. And we see that these are pretty consistent. And the model is doing quite well here. Okay, so now after the model is done training, I'm simply going to stop this. The next step is to perform inferencing. So now we're interested in zooming to a slightly different area. For instance, if I go to my bookmarks and go to inference area here, we'll just select a small area. And it's yet another geoprocessing tool that we can called classify objects using deep learning. Now, if you've trained a model for something like classify pixels, then you want to make sure you use the classify pixels tool. Or if you train a model for object detection, then it's detect objects for deep learning. However, in this case, we're going to do classify objects for deep learning. And then again, I'm going to drag in my raster. I'm going to select my input features. Now, this is going to be your building footprints, right? And because I already have access to these building footprints, I'm simply going to drag these in. You'll notice that these are not classified yet. So this is just a shape with no information about whether or not it's damaged. And then that model definition, this is where that DLPK file comes into play. So I'm going to drag and drop this DLPK file in here. And then I'm going to maybe, okay, leave batch size as 4. Go to environments. And this, again, is where that cell size is very important. We want to make sure that we use the same cell size as what we've selected before. So 0.3, I believe, is the one we've selected. And then processor type, again, we want to use GPU to make sure things are speeded up a little bit. And then since I only want to perform inference over this small area, I'm going to set my extent to current display extent. And then I'm going to click run. So this is going to take a little while to run. We'll see if it finishes, but in the meantime, I just want to show you what that result looks like, because I ran this earlier, and these are the results. I'm going to turn off all of these other layers, and we can zoom in and see how well the model is performing. So we can see that these two houses have been classified correctly as damaged. These other ones are green, meaning undamaged. Honestly, I would say it almost looks perfect. So, given, I think it was 1,000 examples, we're really able to, have the model generalize quite well to unseen areas. So what you've just seen is the entire process of preparing your training data, training a model, and then performing inferencing for the task of object classification, right? Simply slapping a label on top of objects.
Hey,
However,
David?
Yes.
Sorry, there's just a question before we go away from dialogues that we're on about what value you might put in for the parallel processing factor if it's needed if you're only using the GPU.
Yeah, that's a good question. Currently, I believe the parallel processing factor is not really used for these deep learning tools. This is more of a generic parameter that's useful in some other geoprocessing tools, but not necessarily this one. So in this case, I think training currently only works with one onboard GPU. So yeah, this is not a parameter that we have to worry about right now. Yeah, but good question. Typically, by the way, if you want to fully leverage your GPU, I'm just going to show my task manager again, and you'll see that since I've selected a batch size of 4, you should see my dedicated GPU memory usage be stable at a particular level. So this is telling me right now that I'm really only using half of my GPU memory. So I could probably get away with setting this to 8. And in fact, it's finished running. So depending on the size of your GPU memory, honestly, I only have 4 gigabytes of GPU memory, which is not that great. Ideally, you want to see something like 12 gigabytes, or if you have an even beefier GPU, 32 gigabytes of onboard memory. And that allows you to be able to select a bigger batch size, which means more stable training and also faster training time. Since my GPU ID is 0, is it using the Intel instead of the NVIDIA? Not really. So GPU ID is for if you actually have more than one NVIDIA GPU, then that would be the, what this number represents. If I have 2 NVIDIA GPUs, I can select between 0 and 1 here. But yes, it's only ever using the NVIDIA GPU, because the Intel onboard GPUs, they're not really able to run these kinds of CUDA processes. So any deep learning workflows cannot be run on Intel GPUs. And yes, we do see, in fact, that the results are coming in now. So can sort of zoom in to this layer. And I just want to show you that this is the same result as we've gotten earlier. So I'm going to set unique values. And for the field, I'm going to select class label. Not going to play around with the symbology too much, but as you can see here, this is, it's the same result, which is pretty good. Okay, so that's one example. And I do just want to quickly mention that a question that might come up is, for this particular example, we have access to the ground truth building footprints. Well, what if that's not available, right? Then I want to show you how we can use the models that are available on the Living Atlas. So if you just go to Google, search for Living Atlas, click the first link, and then the keyword here is either deep learning or DLPK for deep learning package. And we can see all of these models are ready to use that you can just download straight away. And we have models for building footprints. I'm just going to click on that, open it in a new tab. Before we use any of these models, it is important that we go in and really thoroughly read the description here, because sometimes there's requirements on the types of imagery that this model expects. So for instance, this particular model has been trained against 8-bit 3-band imagery at 10 to 40 centimeter resolution. So you want to make sure that this is the type of resolution that we're using in our inferencing imagery as well. And if we don't have that, then we either have to downsample or upsample, because otherwise the model is not going to do as good a job. And to download this model, very simple, just click download, and you'll see that what is being downloaded is just a DLPK file that you can just drag and drop into your detect objects using deep learning tool inside ArcGIS Pro. So I'm not gonna do that. I'm just gonna show you. I just wanted to show you that it is available here, and we have models for all kinds of things really. Okay, so that's the first example. The second example, I wanted to just quickly talk about another type of data sets that we're using, which is LiDAR point cloud. And let me see here.
David, just a quick question before we go away from buildings. I remember
Sure.
you and I, before this event, we were talking about using some of these change detection tools to see where there's new building footprints, if there's been any sort of like construction or development in our cities. So would we use that same building layer, or can you just, is it really quickly to just show folks where to go if they were interested in that kind of building change detection?
Yes, absolutely, absolutely. And well, that's actually another demo I was going to talk about. So I think I'm just gonna
Oh, okay, I didn't know if we
run
had
that
time
demo
for
straight
them
away.
all.
No worries. That's actually a really good question, because I think the traditional way that people tend to do change detection is by doing something like building footprint extraction across different at different times, and then simply comparing those results, right? Which is not necessarily the best way to go about this, because sometimes, especially for features that are a little bit more difficult to detect, it can be confusing what constitutes meaningful change. And what do I mean by meaningful change, right? So for instance, if we look at this imagery layer, I'm going to use the swipe tool here just to show you the difference between two imagery layers. So we have before and after. Now, meaningful change can mean different things depending on use case. So for us, it might be buildings, but it might also be roads, right? You might also be interested in new roads that are coming up. However, things like vegetation changes, like you see here, might not constitute meaningful change. So as humans, we've built this internal representation of what meaningful change is depending on the different context. So can we train a model to do the same? And the answer is yes. So we actually have a specialized model called the change detector that can do exactly that. And if you're interested in finding out more about the specifics of the model, again, I think a good place to go to is the documentation page for the Python API. So if we come down here, and I believe there is a model summary here called change detector. Let's see, change detector. Okay, so it's under pixel classification. Under the pixel classification models, we have one called change detector, and it's based on a particular paper that, if you're interested, you can always read. But this is a model that is going to label individual pixels for you, dependent on whether or not there's meaningful change. So I just want to show you what that output looks like. And just to maybe quickly go over the training process too, it's almost exactly the same. Again, you're running something like export training data for deep learning first. And then you're trying to export that training data for your before imagery and also for your after imagery. And then the same thing for your labels, right? I just want to show you what the labels look like. So these are the ground truth labels. So these are the labels that we've manually gone ahead and drawn whenever we see a new building pop up. So in this case, we're only interested in detecting buildings, not necessarily roads. And then to train a deep learning model, it's again the same thing, right? Train deep learning model. So I'm not going to go over that too much, but yeah, inside model parameters, we can select the change detector, which is available here. Change detector, here it is, right? So the same process. But I want to show you the model outputs, which I think is the really cool part. So I'm going to go to a slightly different extent here. Yep, and unfortunately it's frozen. No, it's not. Okay. Zoom to layer. Okay, so here's our new extent. So this is an area that the model hasn't seen before. And if I swipe here, you'll see that there's a ton of change, a ton of construction that's been happening For instance, over here, right, we see new buildings come up. And traditionally, if we're doing just pure pixel subtraction, we might get a lot of headaches where, for instance, because the coloration is different between buildings, those might be considered change, right? For instance, all of these buildings somehow look completely different, even though we know that they haven't really moved. So this is where having a deep learning model that just does change detection is super helpful, because then I can turn on the inference result, and this is what that looks like. So as we can see, the results are only indicating locations where new buildings have popped up, right? As opposed to highlighting things like coloration changes or vegetation changes. So this is what we consider meaningful change. And if I use this layer, I think this is a little bit more telling here, right? We see hardly any coloration on top of existing buildings. Really, it's only new areas where we see development that we have these colors. So yeah, that's the change detection. It's simply yet another model that you can use in the same way as you would use any other deep learning model within ArcGIS Pro. Pretty neat stuff. Okay, so that's that demo. I think now, given that we don't have too much time left, I want to quickly talk about LiDAR. And the particular example that we're going to cover is for vegetation encroachment. So vegetation encroachment, as you may or may not know, is one of the primary causes of power outages here in the US, but also elsewhere in the world, particularly for Australia. And they also have a pretty big problem with wildfires. So it is important for us to be able to automatically assess whether or not a tree is encroaching upon a power line. And so how can we do that, right? Because traditionally, the way that this is done is that people would actually drive out to survey their power lines and then visually identify trees that may be encroaching upon those power lines. With deep learning, it becomes a lot simpler because we can train a model to detect trees. We can even classify those trees according to their distances to the power lines. For instance, red indicating pretty high severity. We see the encroachments already happening. Orange and yellow being, places where we might want to keep an eye out for. And then also other attributes, as you have seen, can be very easily detected, right? So for buildings, for roads, for even assets, existing assets like utility poles. And this is quite interesting because you might not think this is something that machine learning can do. But the great thing is we can detect shadow artifacts. And so in fact, we've trained a model to simply detect the shadows for these kinds of utility poles. And they do quite a good job for returning these locations. And again, the power of deep learning really comes in if you have to do this at a very large scale. So this is the city of Manchester in Connecticut. As I zoom out here, you'll see just how many examples we've been able to capture, about 500 miles of power lines that are potentially in need of service. Okay, so this is for a 2D case. Well, we've just been talking about 3D. Obviously, if we have access to LiDAR point clouds, it's going to make things a lot easier because LiDAR tends to be way more granular. You can also better understand the type of encroachment that happens with LiDAR because not all encroachments are equal. And what I mean by that is sometimes with LiDAR, you see that encroachment happens from below, and sometimes you see that encroachment happens from above. And those generally tend to be way more dangerous because branches can always fall and make contact. And obviously, the most dangerous type of encroachment is when you have branches that are already intertwined with some of these power lines. Well, it doesn't help to only say that without really understanding what class each point belongs to. And that's why using, again, some of the existing pre-trained models that we have on the Living Atlas for detecting power lines, for detecting vegetation, and so on, we're able to classify this entire scene into ground points, vegetation, buildings, utility poles, which you might not see very clearly, but these are also identified as a separate class, obviously power lines. Some other neat stuff that we can do is almost, create a 3D scene out of it by turning these points into 3D geometries for buildings. And then this is where it gets interesting, because now we get to visually identify locations where these points are underneath the power lines, so it's actually not that dangerous, versus something like this, where we have branches directly on top of these power lines, or even worse, when we have intertwined vegetation with the power lines. So these are the areas that you need to start trimming immediately. And again, these are the types of things that, you know, a person obviously would be able to do quite easily. But the whole appeal of using deep learning here is that you can do this at a very large scale, consistently, and also frequently. So this is the city of Ballarat in Australia, and we've been able to perform classification over the entire city in a matter of hours using deep learning, as opposed to days and weeks if we were to do this completely manually. And how can we do something like this, right? Again, it's through ArcGIS Pro or through the Python API. And ArcGIS Pro actually provides you a ton of out-of-the-box classification methods for these types of point clouds. Because as long as we drag in these point clouds, I can click on one, and there's actually a tab now called classification. And we see automated classification. These are actually non-deep learning methods to classify points, but then we can classify things like ground and buildings quite well just by taking a look at their geometries. So let me show you what that looks like once you have classified the ground. Now we see all the ground points being classified. And then the second step is classifying the buildings. Now, if we're interested in classifying more custom features like power lines and vegetation, that's where we need to bring in some deep learning models. And then we do see a tab here called deep learning that allows you to either create your own training data, which I'm not going to cover, but it's basically the same process, or you use one of our out-of-the-box models from the Living Atlas. In this case, it's a geoprocessing tool called Classify using deep learning model. And we can just download one of those models. It's a DLPK file that we can just drag in here and click run. And so let me show you what the result looks like for something like power lines. So now we see these power lines being classified. And I think this is quite impressive because the power lines really is a very, very small fraction of all of the available points here. In fact, I believe for this particular data set, it's less than 1% of these points are power lines. But nonetheless, once we have a good model, then we can detect them fairly easily. And then the same thing goes for vegetation as well. If I click on vegetation points, you'll see now this entire scene is completely classified. And this is the first step that allows us to be able to perform vegetation encroachment workflows. The rest is pure GIS, right? We can simply do things like measure the distance between the power lines and these vegetation points to give us the different class labels on whether or not this is either a dangerous type of encroachment or this is simply something that we have to closely monitor. So fairly cool stuff. And so yes, that's it for my demo for point clouds. Again, if there's any questions, feel free to ask it. Let me see here. I think there's a previous question. Is it ever useful to pre-process the change detection input images, i.e. by making them grayscale, other adjustments to help the model work better? Or is it just better to let the model do its work with the raw imagery data? Typically, we do recommend to not really do any pre-processing, because sometimes it is difficult to understand how certain coloration or certain bands might be helpful for a model in a way that we don't fully comprehend. And it's kind of a scary thing to say, but especially if you have like multi-band rasters, then sometimes the model, as long as it's sufficiently complex, can make use of all of those bands. And I don't know if you guys noticed, but then when I was training a model earlier, there's an option for me to choose the backbone. So under advanced, there's a backbone model that we can choose. And if I expand this, you'll see there's a ton of different backbones. And what a backbone is, you can simply think of it as how many layers a model has access to. So 152, you can roughly translate that to 152 layers to a model. So this is a way more complex model that's going to be able to leverage all of the available information that you send it, versus something like ResNet 18. If it's a very simplistic model, then maybe it is helpful to pre-process the imagery if there's a ton of noise in that imagery. But sometimes I think the best approach here is to start with something like 152 and see if the model works. And if it doesn't work, generally there's a trial and error process that happens with these kinds of deep learning models where if it doesn't work, then maybe we can try to reduce the number of bands, or maybe we can try to clean it up a little bit. But also, it is important to note that whenever we clean up our imagery for the model, we have to make sure that the same process is done for inferencing imagery as well. So it could be a hassle, right? If we want to perform inferencing at a very large scale, then we have to make sure all of the same processing is done so the model doesn't get confused. But yeah, that's a very good question. Okay, with that, I think there's only a few minutes left. I do want to just quickly cover Rgs Notebooks, because that is the second route for us to be able to perform training and inferencing. I saw in the poll earlier that some folks have already started using these kinds of GeoAI models, and I think that is it is a crucial skill to learn how to do the same type of work, except inside a notebook. So a notebook is simply this, right? It's something that you can drag into ArcGIS Pro, and it's just a series of Python commands. And if I scroll down here, you'll see a very simple example for detecting swimming pools. So this is a classic case of object detection, because we're returning bounding boxes around our objects of interest. And I just want to show you the parallel that we can draw between the Pro approach versus the notebook approach. It's really the same thing, because the first thing that we're doing is exporting training data for deep learning. And this is a simple command that you can execute. I don't know if this comes across clearly on the screen, but it's export training data, and it's a function that you can call. And it's exactly the same as the geoprocessing tool that we saw earlier, with the same parameters that we can provide, like what is the chip format, what is the tile size, what is that metadata format, and so on. So once this is done, what this is going to return is a fast.ai data bunch, and you don't really have to understand what that means, but this is something that we can visualize. The great thing about doing this directly within the Python API is that before you do any kind of training, you can visualize your data very easily and very quickly, just to make sure everything is correct. So for instance, we can visualize the labels directly on top of the images in a way that we cannot do inside ArcGIS Pro.
Hey, David, are these notebooks available through the Living Atlas? I mean, maybe not with all the parameters, but sort of stubbed out for you?
Good question. It is all available through the ArcGIS API for Python, I think, developers site. So I'm just going to go to Google, search for ArcGIS API for Python. And then earlier we were looking at API reference, but now let's click on samples. And here you can download all of these samples. Unfortunately, you cannot download individual notebooks. You have to sort of download this entire repository. But don't worry, that's simply just a zip file that you can click and download. And the relevant notebooks are inside this this category here called GIS analysts and data scientists. And if you want to search for anything that's related to deep learning, let's just search for the keyword deep learning. And that's the notebook that I was using earlier, detecting swimming pools using deep learning, but also other ones too, right? Like land cover classification and so on. And these are all runnable out of the box, which is great, because you have all of the data available through these notebooks. It's very well annotated. And also for some of these notebooks, I believe there was the option to run this live. I think it's only for a few notebooks though. But yeah, this is just a great resource to check out in general. And so one of the ways to open up these notebooks obviously is through ArcGIS Pro, but just also want to quickly mention that it is possible to do the same through Notebook Server, right? If you have access to Notebook Server. But coming back to that notebook, I just want to quickly show you the rest of it. One important thing here is the learning rate. So the learning rate, think of it as, whenever the model calculates a loss value, how much does it turn its internal parameters so that in the next step it does better. So if we think of a model as all of these tunable knobs, for every single step, how much we are turning that knob. And then obviously you want to set the right parameter for it, because sometimes if you're not turning the knobs enough, it takes forever for the model to learn. Sometimes if you're turning the knobs too much, then it can actually overshoot, and it'll sort of bounce around and it doesn't learn at all. So fortunately, there is a way to do this easily and programmatically. It's called the learning rate finder. This is just a function that we make available through the RGS API for Python. And then to train the model, it's just one line of code, model.fit, and that's it. And these are the types of loss metrics that I was mentioning earlier that you should see start to decrease over time for both training and validation loss. If you see them decreasing over time, then it's an indication that the model is learning. Are there any limitations on the usage of the model outputs? So by the outputs, if you mean the predictions of the model, those can, as I scroll down here, those can really just be exported as a feature layer. They can be downloaded as a shapefile. So really whatever you can do with a shapefile. And the other outputs are the model weights, right? So the trained model itself, and that's going to be your DLPK file. And then whenever you see this DLPK file, just know that this is something that you can upload to Enterprise, right? So you can use this directly within Enterprise. You can share this with someone else for them to perform inferencing and so on. Hopefully that answers your question.
David, you mentioned notebook server. ArcGIS Online also runs notebooks and has the ability to have like an advanced notebook. Can you do that run the same notebook in ArcGIS Online with, of course, a credit cost because it's running a GPU and all?
Yes, you can. That's a good reminder, actually. Yes, that's a capability that's now available.
Great.
Yep.
Great, David, thank you so much. I think just looking at the time, I just at least need to acknowledge that we still got a lot of folks on the call, which means there's definitely an interest in this, and really appreciate you, David, sharing all this information. And I'm still curious to see, there was 3 folks in the crowd that said that they've used these, that they've used this before. So maybe that's something we can do, like a follow-up, so that people can share some of their work. Or I'll give another shameless plug for the call for abstracts for our fall conference. If people want to share, seems like there's definitely an appetite for folks to check out these incredible tools. So, David, is it all right if I share your email address with attendees so that if they have questions,
Yes.
they can follow up with you?
Absolutely.
Fantastic. Yeah, thank you again so much for this presentation. And I will send a follow-up to everyone with the recording and with some of the links. But yeah, if anybody has any other questions, please do feel free to follow up with David afterwards. Thank you all again so much.
Thank you, everyone.